In this video, we'll be discussing multiple linear regression as our extension from simple linear regression. Now, multiple linear regression is just a new extended tool from the simple linear regression that allows us to look at a wider variety of situations by including multiple variables in the model, multiple independent variables in the model. Now, it's important to note that multiple linear regression is different than multivariate linear regression. Multiple linear regression refers to the number of independent variables in the model typically being more than one. So with a single independent variable in the model, we have a simple linear regression. With multiple independent variables in the model, we have a multiple linear regression. However, in multivariate linear regression, we don't have, or sometimes we do have multiple independent variables, but multivariate tends to speak towards the number of dependent variables that we have in the model. So multivariate linear regression would indicate that we had multiple dependent variables in the model, which is not something that we'll discuss in this class. I say this, but I do note that in some journals, they discuss multiple linear regression using the terminology multivariate linear regression. In fact, on some papers I've published or submitted for publication, because that's the habit of the journal, I too have submitted it like this, because when I'm submitting in a journal that does this, I use the terminology that the client that I'm working with uses in their field. So that's typical definitions. The one that we've talked about are primarily for people who are familiar with statistics, but sometimes in other fields, this distinction isn't made quite as clearly. Now, the data for multiple linear regression is very similar to what we've seen thus far. Y sub I is still a response variable for the ith individual, but now we have p-1 explanatory variables, and we're not limited to just one independent variable anymore. So what you'll see is that we have x sub 1, x sub 2, x sub 3, so forth. Notice in the notation that I use x sub I and then the number of variables. So x sub I for the ith person, and then that's variable 1. Sometimes you'll see this reversed, so what you'll look at is what are the variables noted and then what are the different cases noted as in determining this. But in this class, this is what I'll tend to use. So for an example of this kind of model, just right at the beginning, big picture ideas, consider predicting freshman GPA based on high school GPA, ACT scores, and IQ. So in this particular case, what we would have done previously in simple linear regression is predicted freshman GPA, and we might have had three models. One which uses ACT score to predict freshman and college GPA, one which uses high school GPA to predict college GPA, and one which uses IQ to predict college GPA. Now what we're able to do with multiple regression is incorporate all of these independent variables in a single model which predicts this outcome. In this problem, we have p equal to 4. So consider that we have 3 independent variables, but 3 is the number p minus 1. So the number of explanatory variables is p minus 1. P actually stands for parameters. So in this case, we have 1, 2, 3 independent variables, but we actually have 1, 2, 3, 4 parameters that we need to estimate because we need to include the intercept, which is not an independent variable. So p is just the number of explanatory variables plus 1, or p minus 1 is the number of explanatory variables. So in the scalar multiple regression model, similar to what we just saw, we have y, we have all of our parameter estimates. Note that we use betas with our x values, and that we just increase the subscript of the beta as we add more independent variables to the model. We go up to p minus 1. And then we still have our error term for each of the I cases. I is still the number of cases from 1 to little n. The assumptions are phrased exactly like before. We'll talk about them in a second, with the errors being independent and identically distributed as a normal with a mean of 0 and constant variance of sigma squared. The yi is still the value of the responses, and the x sub ik is the value of the kth explanatory variable for the ith case. And again, depending on which notation you see, sometimes these are switched around, but in this class we'll tend to try to use that particular notation. So what are these different aspects? Well, B0, just like before, is the intercept. But now, because we're dealing with multiple independent variables, this is no longer the y-intercept in the same way that we would think it. It's the multidimensional intercept that happens when all of the other variables are equal to 0. So we now have multiple independent variables. All of those independent variables are 0. That's what beta 0 is representing, when all of the independent variables are 0. Now, each of the other betas represent the slopes in exactly the same ways as what they did before. The interpretation is slightly different. We'll talk about that in a bit, but the basic idea is very similar to what we had in simple linear regression. As before, we're going to be estimating the betas and the variance term, sigma squared. So we'll get all of our b's, and then we'll have that MSE term that we use when we look at the statistical significance. Now, when we're looking at the prediction, we no longer have a prediction line like we did before. So before we had a single x value, that was our x values on the graph, and then we had a y value, that was our y values on the graph, and it was 2 dimensions. And when we graphed x versus y, we got a line. So recall that a line was in 2-dimensional space because we had one independent variable and one dependent variable. When we have 2 independent variables and one dependent variable, now we have 3 dimensions, so we're going to be graphing in 3-dimensional space. So to graph a 2-dimensional object in 3-dimensional space gives us a prediction plane instead of a prediction line. Now, if we have 3 independent variables, then we're in a 4-dimensional space, hypercube, and we're graphing these hyperplanes onto the 4-dimensional space. So as this goes up, these become more and more difficult to see. I'd say 2 independent variables is probably the last one that we can see. We can create 3-dimensional prediction planes in R if we wanted to. I'm not sure that we'll talk about that in this class, but it is a possibility, and it's kind of fun to do, to create some 3-dimensional objects in R just to see what it looks like. But as we go above 3 dimensions, it becomes very difficult for us to discern what's even going on. So prediction plane is for 2 independent variables, but it goes on and on and on as we have more independent variables, and we kind of stop thinking about in this terminology. We just start thinking of prediction as a general term. All right, now recall that the first step when we're implementing a model is to check the statistical assumptions. So that's our very, very first thing to do when we're looking at a model. It doesn't change when we're in multiple linear regression. So the assumptions of multiple linear regression are the same as the assumptions for similar linear regression, or very, very similar. And we're actually, because we very cleverly used the y-hats in our assumptions, checking our assumptions for simple linear regression, are going to be able to use the same thing in checking our assumptions for multiple linear regression. Recall in our conversation of checking assumptions in simple linear regression, we discussed how you could use x in place of y-hat when checking those assumptions. Once we're in multiple linear regression, that is not the case unless we're looking at the contribution of the violation of the assumption within particular independent variables, and that's a concept that we won't discuss maybe in the very last class, but I don't think we'll get there. Now, in multiple linear regression, there is one additional assumption in addition to all of the normal things that we tend to check in simple linear regression. So things like outliers, things like linearity, independence, normality, constant variance, all these things are the things we tend to check, but there's one particular new one that we have in multiple linear regression, and this is called the assumption of multicollinearity. With multiple predictors, the challenge then becomes that sometimes these independent variables are correlated with each other, and that can lead to some problems. If predictor variables are highly correlated, the problem is that each predictor is trying to explain the same amount of variation, or the same chunk of variation in the outcome. We'll have a nice graphic in a bit to explain this. But when each of the predictors are trying to explain the same chunk of variation in the outcome, what ends up happening is that neither of the predictors in our model explain much that isn't also explained by the other variable. So when we look at the independent contribution of a variable, it doesn't seem to have much of an independent contribution because most of its contribution to the model is shared with another variable. And this is the idea behind multicollinearity, that highly correlated independent variables fight to explain the same variation in the outcome. Now, when using highly correlated predictors, the problem that happens is that our parameter estimates kind of suck, quite frankly, because the parameter estimates are based on the independent contribution. This really throws off our statistical tests of parameter estimates and the use of statistical tests to determine if a particular independent variable is actually related to the outcome. However, this doesn't really affect prediction. So what we're really looking for is we have to be pretty careful about multicollinearity when we're implementing a model and using it to determine which of the independent variables are statistically significantly related to the outcome. However, if we're just trying to predict the outcome, we don't have to worry about multicollinearity quite as much. So again, this is the picture I was mentioning earlier. On the left, we see a indication of a multicollinearity situation, which is where x1 is actually reasonably related to the outcome. We see the overlap between the yellow circle and the purple circle here. And then x2 is also reasonably related to the outcome. We see the overlap between the green circle and the purple circle here. But the x1 and x2, the portion of variance they explain in y, that is the portion of purple overlap that each of these circles have, is very overlapped with one another. So when we actually look at the unique amount of y that is explained by the yellow circle, it's just this little kind of bent pie-shaped chunk up here, which is much smaller than the total relationship that it actually shares with y. Same thing with this green circle, that when we look at the independent contribution that x2 has in explaining y, it's just this bent pie shape down here, which is just a small fraction of its total contribution. This is a great visual example of multicollinearity and why, given the fact that our statistical test the independent contribution, both of these might come out in a multiple linear regression as being statistically insignificant, even though in reality both of these are highly related to y. And the reason is that both of these in their relationship with y share that relationship with one another. Now contrast that with a case with no multicollinearity, where x2 is related to y in this large chunk, but none of that chunk overlaps with x1. x1 is related to y in this large chunk, and none of that chunk overlaps with x2. In this particular case, this is a fantastic case for multiple linear regression because our variables don't overlap with one another, and we don't have an issue of multicollinearity. And again, it's important because our statistical tests assess the independent contribution of each variable. That is, in this graph, it's the complete overlap between purple and blue, the complete overlap between purple and yellow. But in this graph, it's just these little pie-shaped where the purple and yellow overlap, but the green isn't there. And this other little pie-shaped piece for x2 where the purple and green overlap, but the yellow isn't there. That's what we're assessing the contribution of in this left-hand model and in the right-hand model. Multicollinearity is also often assessed, almost always assessed, by the use of a statistic called the VIF, or the variance inflation factor. Sometimes you'll see the term tolerance. This is just 1 divided by the VIF, or the inverse of the VIF. So sometimes, I mean, if you see a paper that uses tolerance instead of VIF, that's what they're talking about. Now, the VIF is actually really straightforward to calculate. Pretty much what we do is a regression, but we treat each one of the predictors as the outcome. So in this case, in the general case, I'll take out predictor x sub k. So this is just one of the independent variables that I'm going to treat as the outcome, and then I will do a regression of the rest of the independent variables on this independent variable. So the idea is if this independent variable isn't related to the rest of these independent variables, then all of these betas are going to be 0, and my r squared, the proportion of variance explained, is going to be 0, or very small. So the VIF is just going to be 1 divided by 1 minus the r squared from this model. Now note that we're going to get a VIF for every single outcome. So we do this for x1, x2, x3, x4. We do it for every single independent variable, excuse me, not every outcome, every independent variable. We do this for every independent variable included in our model, and that gives us p minus 1 VIF values. Note that we don't do it for beta 0. So p minus 1 VIF values, and we look and assess each to determine which variable seems to be made up of a linear combination of other independent variables. And if that's the case, again, that's our case where we have a meaningful correlation between a linear combination of the variables, and that's something that we don't want to have, or gives a higher risk of misinterpreting the tests of statistical significance. Note that we can calculate this in R pretty quickly. There's just a VIF function that you apply to your linear model from the CAR package that you can use. Now we can also assess multicollinearity in a couple other ways. We can use a correlation matrix just to look for correlation among independent variables. I think we'll do this in our R example. And then we can use pairwise scatter plots. We'll also do this in our R example, demonstrating how we can look at the linear relationship between variables to see if there's a potential concern with multicollinearity. To fix it, well, first of all, when do we need to fix it? So when we don't like high VIF numbers, that indicates a strong degree of relationship among the independent variables. That's what we don't want. So high, I say greater than 5. I mean, it depends on who you ask. So maybe, there's a whole bunch of different criterion. So typically 0 to 3 is pretty good. 3 to 10 is meh, and then above 10 is really bad. But maybe as a rule of thumb, if you just wanted a single cutoff, greater than 5 would indicate a good spot for a change. Anyway, when VIF is sufficiently high, whatever sufficiently high means, there's a couple of ways that we can fix it that we won't go into detail. First of all, and actually I don't have it in my little list here, so you'll just have to make a note in your notes. The first option that we can do is we can look at the variable that has the highest VIF and then remove it and run the model again and see if that works. So that's a pretty common way to approach it, but it doesn't tend to be really driven by much. It's just driven by that VIF statistic, which can be slightly problematic. A couple better methods would be to remove one of the factors, maybe which theory says. So if I have a theoretical reason to believe that this one variable is a linear combination of the rest of the variables, then maybe that's the one I remove. Or we can use some maybe more robust methods such as ridge regression or lasso. Lasso's probably be my pick among these to reduce the coefficients down to 0 so that we don't have these. We have the particular contributions for the variables that we're interested in and actually have a relationship with the outcome. The other thing that we can do here is combine the factors that seem to be highly related into a single value using a technique called, there's a couple different ones, principal components analysis or vector analysis. So these are both options that we could do to fix multicollinearity. I'll note that these are discussed in more detail in our Intro to Machine Learning course, where we actually have a chapter on both of these, a chapter on dimension reduction and a chapter on ridge regression and lasso. So if you're interested, feel free to check out that course. All right, so our model in matrix form, we kind of talked about this previously. Nothing's really changed here, where we have the vector y equals the matrix x, the design matrix, you'll hear that called, times the vector of betas plus the vector of errors. The errors are normally distributed with a mean of 0 and a variance covariance matrix of the constant sigma squared times the identity matrix, n by n identity matrix. And then the vector of y's are normally distributed with a mean of x beta, recall this is y hat, and then a variance covariance matrix of sigma squared times the n by n identity matrix. The design matrix, just to write it out again, is our list of ones, and then we have the different lists of our x. So previously we just had list of ones and then our first x value, but now that we have multiple parameters, we're going to just add columns of x values for each new independent variable that we have. The coefficient matrix, beta, is now just going to add in coefficients for as many independent variables as we have, all the way to p minus 1. So we'll just add these on as we have independent variables to add into our model. And then all of our solutions stay the same, which again was the whole point of doing all the work in matrix form. So for the least squares, we now want to minimize the distance between the point and the response surface instead of the line, or if we're going multidimensional, again, we just don't really touch on the terminology for that. So we'll just say minimize the distance between the point and the prediction. So we still find our parameter estimate vector in the same way using the sums of squares as y minus the design matrix times beta transpose times y minus the design matrix times, I should say beta hat or b. So this is the SSE just like before. And we get the same exact normal equations as before. And again, we talked about in the matrix lecture why this is the case and how, because the dimensions are conformable, that's the whole purpose of writing this in matrix form, is that this is a very nice handy solution. I will note that all these things are bolded. The x transposes and the x's are matrices and the y and b are vectors. So for the fitted values, we have y hat as xb, which is the hat matrix times y. Residuals are y minus y hat, just like before, or identity matrix times the hat matrix, or identity matrix minus the hat matrix times y. The formulas, again, are all exactly the same as before. Our hat matrix is exactly what we saw it was before. So recall that the term linear, as we're working through this, is not a line, right? In fact, we talked earlier that our regression prediction, if we have two independent variables, is no longer a line. Now it's a plane. So the term linear is referring to linear in the parameters, not the predictor variables. Because of this, we can use almost any function of the predictor variable. So we're going to be using things like x squared and log x as predictor variables, and that is completely okay and still considered to be a linear model. Not a linear relationship, but a linear model. This said, we can't use linear regression models to deal with nonlinear functions. The exception to this rule is if we have a nice transformation that makes them linear, then we can deal with it. But as a rule, with nonlinear functions of the parameters, that's not something we can address with linear models. So given this, we've got several different types of predictors that we can use. The quantitative predictors are just the numerical independent variables, which is what we've dealt with before. We can also deal with qualitative or categorical predictors, kind of like a binary coded male and female, which we'll code, dummy code, effect code. We'll talk about this in the next chapter. But this actually becomes a little bit more useful in multiple linear regression, because typically if we were doing a simple linear regression with a categorical variable, we would either just do a t-test or an ANOVA, depending on the type of categorical variable and how many levels it had. We wouldn't do a regression, though statistically they're the same thing. But now that we're into multiple linear regression land, it actually becomes really convenient to be able to drop in categorical independent variables into our model, which already has continuous independent variables. So this is something that we'll talk more about in future videos. Now, we spoke earlier about the idea of being able to drop in nonlinear relationships, this being polynomial regression. This is a huge jump forward. Now, there's some problems here that we will talk about it at some point in the future, but this is a huge jump forward in what we are able to model, this idea of polynomial regression and nonlinear models, or excuse me, nonlinear relationships being modeled with a linear model. So we can use squared or higher order terms, but the rule is, and this is something we haven't talked about before, that if you use let's say a cubic term, then you have to include all of the former terms. They're called the lower order terms. So if I use x squared, then I have to also have x in the model. If I use x to the fourth, then I also have to have x to the third, x squared, and x in the model. So if you use a higher ordered polynomial term, you need to include the lower order terms, even if they're not statistically significant. So for instance, if I wanted to do a cubic term, this equation where I just had the cubic term would be inappropriate. And actually, this is something we used in a previous video. I didn't really talk about it because we were making a bit of a different point. It was in the context of discussing linearity, but just dropping x to the third in the model is pretty inappropriate. Actually, what this does by default is it assumes that beta 1 and beta 2 are 0. So when I don't include terms in the model, that assumes that their coefficients are 0. To not make this assumption and to make sure that I'm incorporating the cubic term properly, I need to include the lower order terms. That is, I need to make sure that x and x squared are included in my statistical model if I want to include x to the third. Even if these do end up being 0, I still need to include them because I don't want to constrict them or force them to be 0 by assumption as opposed to being 0 by observation. A couple other types of predictors. This is one that you've seen before, the transformed variables, where we can transform either the x's or the y's. One last important one up there with polynomial is something called an interaction effect, and we will talk about this much more later. Sometimes interaction effects study what are called moderating relationships, and we look at the variable that causes the interaction as a moderator. But in interaction effects, we use the product of two or more independent variables as an additional variable that is called an interaction effect. So literally, let's say we have x1 and x2 in the model. We multiply x1 times x2 and use that as a third variable in the model, and that x1 times x2 is called the interaction effect. Now when we do this, just like when we have polynomial models, we need to include all of the lower order terms. So if I have the interaction between x1 and x2, then I need to make sure that x1 just left alone is in the model and x2 just left alone is in the model, even if they're not statistically significant. Again, this is similar to if I have a cubic term in the model, I need to make sure I have all the lower order terms in the model. Now, when I talk about the x1 and x2 just left alone, the terminology for that is main effect in comparison to the interaction effect. So the main effect would be x1 and x2, and then the interaction effect would be x1 times x2. For an example of an interaction effect model, we have y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3, and then the interaction x1 times x2. And this is literally mathematically x1 times x2. I tell you, when I first learned about these models, I didn't believe it. I thought this was some voodoo magic, but this really is all it is. So in this, I would call this beta 3 the coefficient of the interaction term, and then beta 1 and beta 2 the coefficient of the main effects, or the main effects from this model. And we will talk much more about interaction models later. Their interpretation is tricky. The interpretation of main effects in the presence of an interaction is tricky. So this is a long-term conversation that we were just beginning, but this is the definition of what an interaction effect is. All right, well, we'll call that for this video. In the next video, we'll pick up on ANOVA and some of the different predictions and statistical tests that we can run, and then we will jump into how we actually start interpreting these different components of the multiple linear regression model.